Hello, everyone. So the objective of this video is to show you how to fit fluorescence binding isotherms using MeltR. If you haven't already, I would definitely get the manual from the website and read through that, make sure you understand everything. But today I'm just going to demonstrate how a basic workflow would work. Right. So the first thing we want to do is tidy format our data. And the four important, and you can do this in Excel and then save it as a CSV. But the four important columns that you need is the well, the reading, the temperature, the fluorophore labeled strand concentration labeled A, the quencher labeled strand concentration labeled B, and the emission. You can have other variables in here. You might want that for some other reason, but MeltR needs these. And note that it's tidy formatted. So we have all the data points for well A and a 96 well plate, and we go down and we can see all the other wells. But we're using a tidy format. We're not having, every column is a different variable. Every row is a different observation. We're not using a lot of columns. Okay, so we can go ahead and save this as a CSV. I'm going to save it here. And then from here over, if you followed my installation instructions, you should have MeltR installed in your R environment. And I'm going to use RStudio to show you what I would do when I want to fit a data set. So the first thing I'm going to do in RStudio is I'm going to go over here and make a new R script. And then I'm going to save the R script in the same directory as my data file. So here is the data, and I'm going to call this example script.r. Okay. Now the second thing I'm going to do is go ahead and make sure R knows the right place in the computer. And there's, more sophisticated way to do things, but like I feel like new users, this is a good strategy. So I'm going to say find the right place in the computer. Okay. And we can use RStudio to do this. We just go session, set working directory to source file location, and it's going to go to the right spot. If we look down here, it's set the working directory to the correct spot in the computer. Then I can go ahead and copy that, paste that. And then, if I open up the script later, I can go right to the correct spot in the computer. The next thing we're going to do is load in packages. And so, of course, we need to load MeltR. So we type library MeltR, and then I'm going to run that code, and we see it runs down here in the bottom left hand corner of the console. And then I also like to use tidyverse and ggRepel. These aren't part of MeltR, but they help plot the data to make sure it looks good. But of course, you could do this in Prism or Excel or whatever. You don't have to use R. So now we can load in the data. And the easiest way is just to find our CSV. So if we go list.files, it will tell us here in our console in the bottom, what files are available. And we see I have a data set here formatted as a CSV. So I'm going to go ahead and type df read equals read CSV. And then I can copy and paste the file name. And that's it. If we look over here in my environment, I can see that we have a new object called data frame containing our data that we just saved in as a CSV in Excel. So after that, I always want to look at my data. The number one problem that people have with MeltR is trying to fit bad data. So, data that doesn't really agree with a thermodynamic model. Because there's a lot of noise, or maybe they've processed it incorrectly. Maybe they're using the wrong molecular model, but it's always a good idea to go ahead and look at your data first. And we're going to type ggplot. This isn't part of MeltR, but it's a quick way to look at the data. And the first argument is the data frame. And the second argument is going to be, we're going to define the aesthetics of the plot. So we're going to say X equals B for the Quencher strand concentration, and then Y equals emission. Well, I'm actually forgetting what the variables are, so I'm just going to look at the data real quick. So I go head DF, and I see my variables are here, and it's emission. And then I want to filter the data set, so I'm only seeing one reading at a time. And I'm going to say reading from here. If we try to look at all the readings at once, it's going to look like a mess. And what this is doing is it's just filtering the data set, reading equals 1. And then I type geom point. And then I also want it to label the wells. So I'm going to say label equals well. And I'm going to say geom text repel, which is from ggRepel. And I can see my data over here in this little plot window. And the wells are labeled, so I can identify a point that maybe we should exclude from the data set. So it looks pretty good at the first reading. I'm going to go ahead and check another couple readings. I'm going to go up to like reading 40. And we can see that it's starting to melt. So I'm just going to maybe check. I think there's like reading 100 in here. And by then, our isotherms have totally melted. So this data, I think it's looking pretty good. So now we can get to the actual MeltR part, which is the easiest part if you have good data. So I'm going to say fit data with MeltR. And I'm going to go ahead and I'm going to use first I'm going to pull up the MeltR function help file. So I wrote it and I can't remember everything it does. So that's why I included a help file. If you put a question mark in front of the function, it will pull that help file up. This works for all our functions. And we can see a help file with a description, the usage, the different arguments, what they mean. If you're new to fitting your data, you should probably look into this. It's not that long of a read. But what I can see here with the usage is all the other arguments have default settings. So I only need one argument, which is the data set. So I can go MeltR F df. And then we're done. So you can see it fit the data and gave me thermodynamic parameters. Since this worked, I'm going to go ahead and save results all. And this will save results on the disk. If I now look at this folder, we have a whole bunch of stuff. So we have a CSV, which you can open in Excel, full of thermodynamic parameters. We also have a depiction of the global fit. You can see that the red lines are the fit and the black dots are the data points, and they overlap really well. And then lastly, we have this Van Hoff plot. And if we look at this Van Hoff plot, what we want is for this red line to overlap with this kind of straight region here. Too low, we can't really determine a KD. Too high, we can't really determine a KD, but we want this sweet spot to agree. And the way to do that is to adjust two other arguments. The first is KD, error quantile. You can play around this, but basically it will become more permissive and allow more data to go into the fit if you increase it from 0.25. I'm going to go ahead and try to increase it to 0.5. And then I also want to change this KD range argument shown here in the help file. And that's the KD range corresponds to the highest KD value and the lowest KD value. And I kind of want to zoom in on this region right here. And I know because I played with this data set before that I want it to be between about 50 and 500. So now if we look at it, that's not great. We've narrowed in on the range, but now we're starting to pick up some of these points out here that don't really make sense. So we're going to decrease the KD error quantile again to about 0.4. And now look, we've got a line that really agrees with the data. We have quite a few accurate like we fit 14 isotherms. So that's a pretty good data set. We could, if we want to increase the number of isotherms, we can try fitting it again. That increased it to 15. Let's try 48. Okay, about 16, 15. I would like to have about this accurate K's number to be between 15 and 20. And if we go back to the Van Hoff plot, we got good agreement with the data. If we go to the global fit plot, we have good agreement with the data. We're done here. The last thing you might want to do is make a MeltR fit object to extract some other stuff. Sorry, MeltRF fit object to extract some other stuff. Basically, you can go fit equals this, and then we make a new object called fit, and fit contains all kinds of stuff. It's a list. So if we go fit $, here we can see all the things in this list. So for example, you might want to know the TM of each individual curve in the data set. And here we have that. We have the TM, we have the 1/TM in Kelvin for each well, which is pretty nice. We might want the nonlinear regression objects from R. So for example, for the method 1 fit, here we have the nonlinear regression model, the two parameters that came out of it, and we can go summary and get all kinds of stuff out of here. We can go OEF, summary, get all kinds of stuff. So yeah, that's kind of your basic workflow. there's lots of stuff in the manual you can read up on. And if you need anything, please contact me.